The proliferation of commercially available unmanned aerial systems, or drones, presents unprecedented security challenges in both military and civilian contexts. The threat is no longer from sophisticated devices that have been designed to be undetectable. The threat comes from systems based on consumer drones that are readily available and easily put together, that they can appear virtually anywhere. But if bad actors are using consumer drones to keep things cheap, then consumer-grade hardware can see them coming. TTP has developed a proof of concept for a pocket-sized, passive RF drone detector. We've combined low-cost RF hardware and low-power edge AI into a future-proof system that has the potential to protect law enforcement officers, military personnel, critical infrastructure, and large public gatherings. I'm George from TTP's Defence and Aerospace team, and I want to talk you through how the technology works and how it could be customised as a product for different real-world applications. The proof of concept is based on an off-the-shelf handheld spectrum analyzer to collect RF emissions from the C2 link and convert them into a spectrogram. Converting the RF data into a spectrogram allows us to use a convolutional neural network for detection of drone signatures. CNNs are a well-established architecture for vision-based classification tasks, and our lightweight model requires less processing power than a mobile phone. Another advantage of classifying on spectrograms lies in the ability to use large image data sets in a pre-training step, significantly reducing the data collection burden. The device sweeps through large sections of the spectrum at low resolution before conducting high-resolution sweeps on the identified areas of interest. This two-stage approach gives us wide spectrum coverage without needing expensive RF sampling hardware with a large instantaneous bandwidth. The system is able to detect drones in a wide range of noisy and quiet RF environments. The use of CNNs to detect the C2 link of a drone from its spectrogram is not new, but doing so on low-swap C hardware capable of analysing a wide portion of the spectrum without significant computing resource is highly novel. We are also developing a scalable synthetic data generation pipeline, which uses the characteristics of a C2 link obtained from a single recording to generate large quantities of representative samples. A single recording of a new drone type could be enough to update the detector. An advantage of using CNNs for detection is that the models will learn the underlying features of UAS emissions, enabling the potential detection of previously unseen signatures. This gives it the potential to identify unknown types of drones. The detection methodology and the scalable ML pipeline mean that for the first time, individuals can be equipped with a low-cost, passive drone detection device that can keep up with the pace of UAS evolution. In a tactical environment, the detection hardware could be ruggedized with an external antenna located for best signal reception. Adding an end-user device would allow an operator to configure detection parameters and view range estimates for approaching drones. In civilian environments, the detection hardware uses an internal antenna and may look like a power bank. This device could alert the user to a nearby drone through vibrating, allowing them to react accordingly. A larger Power over Ethernet variant could be used to protect fixed installations, integrating seamlessly into the existing security networks of prisons, grid infrastructure, or stadiums.